Now, I'm curious, how many of you tried drawing this thing? Did anyone have a go? Okay, now, let me suggest to you, I'm not going to make you do it now. In fact, I'm not even going to do it myself because you can do it without it. But I'm very surprised that if you're trying to work out why is it that two of these derivatives, both of the gradient functions are the same, even though the functions look pretty different to me. Gradient tells you something about what it looks like, how it behaves, okay? So as a problem-solving strategy in general, I think it would have been a nice idea if you actually gave it a go. And so what's going on here? What about if I'd done this? What would you expect? Now you might guess, I think it might be the same derivative, and you'd be right. The question would be why. Now, before I actually show you, unveil the whole thing, I'll tell you the reason why this is tricky and why it's a bit weird, and why only like a third of you put your hands up as to, yeah, I'm sure it's right. I'm not sure I can explain it, but I'm definitely sure it's right. The reason why it's counterintuitive is because of these guys, right? And the fact that we're used to them being different when you differentiate, yeah? So, for instance, well, bad choice. When you differentiate each of them on their own, slightly better choice. Okay, when you differentiate each of them on their own, are the derivatives the same? No. Are they the same?
No.
They're not, right? Because you'll get 1, 2, and 3. Okay? But the reason why is because when you draw them, how do they look? Okay? Yeah. So, x, what is that? 45 degrees up from the axis. So it'll look like that. How does 2x look different? It's steeper. And how does 3x look? Steeper again. Okay, and that's why their derivatives are different. Okay? But what do these look like and how are they different? Do we need to actually draw them? If you drew them, you'd see the derivatives do match. Okay? How could you work it out without drawing it? It was all there. We started the lesson with it. In fact, because, who was it? Was it Amelia? I think it was Amelia. Started us off actually very conveniently with the law that we needed. That was just a coincidence. I didn't plan that. Seriously, I didn't plan it. Can anyone see it? Who's got the wheels turning? Yeah. Can someone tell me how can I prove, like visually or maybe algebraically, in a way to say it, why the derivatives are the same?
You split it, and so x is actually like the same, but then 2, 1, and 3 are constant kind of thing.
Okay, let's rewind a little bit because I think you're right, but I'm not sure if everyone understood your thought process. You said split it. How do I split it? Okay, good. So a product in here means that's actually the sum. Yes? Okay, are you seeing it now? So this here. There's my 2x, 2x. Okay, fine. So now when I differentiate the lot, differentiate both sides. Okay. Some of you may actually remember, what this value, I think it's 0.693, blah, 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 something like that. Okay, but the important thing is not so much what value it is, but that it's a value, it's constant. Okay, so when you differentiate it, it just becomes 0 plus the derivative of that, which is 1 x. Okay. So this is interesting. The difference between these, 1, 2, 3, is that the slope changes. Okay, but the difference between these, because of how logs work, it's just a vertical shift, isn't it? This would be this plus log 2 up. Okay. What about this one? It'll be this plus log 3, wouldn't it? You just go a little higher. That's all. Okay. All right. So that's that. There's the mystery solved. I'm going to go and have a look at how the chain rule works with log functions, because some of the questions you were having a go at have some quite involved questions. So I'm going to go back and review that because some of you were struggling a little bit. Some of you are fine with it, and that's okay. But I didn't actually derive the chain rule with log functions. It was a bit of a steep introduction. So make that little subheading, and let's think about a question like wants to start? Now, chain rule, or function and function rule is the proper name, but who likes to say that many syllables? Chain rule, how does it work? Well, what's the definition of chain rule, actually? They don't know it. I'll give you a clue. It starts with d1 and dx.
nx and minus root
Equals what? What is it equal to?
nx.
Now, hold on, let's pause for a second. I just said chain rule. So I'm thinking about chain rule with regard to all functions. So completely general. So not pinned down to polynomials, not pinned down to exponentials, no particular kind of function. Any y that I like, okay? What goes after here? It's the chain in chain rule. dy on du times du on dx. Okay, good. Now, that obviously begs the question, what's this new business? We'll get to him in a second, okay? By the way, I should mention, because I've been writing it for a few days now, but I haven't really addressed it. I'm not sure if you're familiar with this, but this is the bad one, isn't it? The dot is multiplication. You probably guessed that already. I'm using it now in this topic because we have so many x's flying around, and for me it's just a bad idea. If I'm actually writing, like handwriting, I tend to write my x's like that. I'm kind of in a hurry, so it looks just like multiplication. If any of you are brave or crazy enough to do maths at uni, you will actually discover that dot multiplication and cross multiplication, which is what you're used to writing, are actually totally different things. And future HSC students are actually probably going to discover that more because it becomes a big deal in a topic called vectors or vector calculus. So when you're looking at matrices and all that, which is in the new national curriculum, dot multiplication of matrices. So for instance, this, if this means anything to you, no, I shouldn't do that. Let's stay with it. Okay. You don't need to know what that is, but that, whatever it is different to that. You're like, oh, my brain, it's not even 8 o'clock. Okay, so anyway, I'm just saying, I'm going to use it for your intents and purposes. Multiplying is multiplying. Hooray, we don't know that there are two different kinds of multiplying. But if you have a bit of a death wish, you can go and have a look at them. They are different. So anyway. Okay, now, I said I would come back to what this u was. I have a y, I have an x. What's the u? We substitute something. What do we substitute? Yeah, good. So in this case, it's this. So colloquially, you might call it the inside function. You've probably heard it called that before, right? Okay. So that's why this is function and function rule. Yeah. So let's actually do the substitution here. By the time you get used to using chain rule, you don't need to pull out the full version. Okay, but if you're struggling a little bit at the beginning, and particularly since these are the first times we're really attempting these kinds of questions, it's worth doing the full thing. So let u equal x squared plus 1. Now this point you have a choice. I generally, now that I have u and x in terms of each other, I differentiate straight away. Okay, because du on dx is half of the pieces that I'll need to get the derivative. And I've got u and x there, so I'll just work it out straight away. Du on dx is equal to 2x. Good. So, there's that part of the chain rule actually resolved. Now I've got this dy and du business, so I need to work out that relationship. So based on this substitution, I can say y equals log of u. So it's a pretty simple example to begin with. I've got this piece, tick. Now I need that piece, dy on du, which we've just established is 1 on u. Well, not just established, last lesson. Okay. Now I'll do one more step just to make sure it's all clean and nice. That u is actually something we introduced artificially. Okay, so I'll put it back in terms of x's. The reason why I like doing that is so when I come to here now and I actually say, okay, what are these two? When you're doing integration by substitution, okay, you guys probably know that you've got to be really, really careful. Okay, you've got to watch out for your upper and lower bounds and so on. So it's a really bad idea in general to have two different kinds of variables flying around at the same time. So I avoid, don't like this, I avoid writing this kind of thing. What did I say? What did I do? No, it's 2x. Okay? It's true, but I think it's sort of not a good habit to get into, to have u's and x's flying around, when really, you're really meant to have one or the other. Okay? And the whole point is to get rid of the u's. So that's why I did this. So instead, I can get it all in terms of one variable. And of course, mentally, most of you are probably up to the stage where you can just write that straight away from here. Because you can see it's in the form, for log functions, f dash on f. Okay? So, let's just tie that up and just link it to integration. I have enough space over here if I get rid of these matrices. Generally speaking, the derivative of a log function involving chain rule. Okay? That's this guy down here. Okay, so you can simply write it as f dash on f. You can go straight there. You don't need to go through the whole substitution if it's a pretty simple question like this. Okay? If you're doing function of a function of a function, it's obviously in your interest to try and break apart some of that working so you're not doing it all in your head. But this is a pretty simple one. Okay? Now, by the way, before we leave off this, every time you know something about differentiation, you equally make a statement about integration, right? So if I were to turn this statement not into a derivative, but into an integral, what would I write? So this is, if you like, right? This is the primitive, right? This is where it came from, and this is what you ended up with as the derivative, okay? So if I just integrate both sides with respect to x, that's this part, f dash on f, with respect to x, what am I going to get the other side? Log of f. Right? Wrong! You're all wrong! Wake up! What's wrong? Thank you. By the way, just in case, probably this has been mentioned to you before, but the way that marking works in the HSC is that there are no half marks given for anything. Even for, really tiny little insignificant errors, right? No half marks, okay? So if you leave this off, one of two things will happen. Either you lose a whole mark, off say like a 2-mark question, you'll get 1 out of 2 even if the rest is fine. Or, if you're lucky, nothing will happen. Because what will happen is they only check for the constant of integration on a single question in the HSC. Generally, it's in question 1. Sorry, I take that back. Question 1's multiple choice now. So it'd be question 11 is where you would see it, okay, generally speaking. So if you're lucky, you'll miss it if you forget it, okay? But if you're not lucky, bam, the whole mark goes, okay? So don't forget it.